Hello everyone, I am Akhilesh Kumar Srivastava from ABS Engineering College, Ghaziabad. In the series of operating system lectures, we have discussed about the memory management schemes. We have discussed about the background for the memory management schemes, why it is required, and then we have discussed about the fixed size partitioning schemes and variable size partitioning schemes. Both of these partitioning schemes have certain demerits, and to overcome those demerits, we have other techniques to be discussed in today's lecture and the subsequent lectures. The background for today's lecture would be that we will first create a background again, or we will see the background of the memory management scheme again, and then we will see the logical and the physical address spaces, and then we will discuss about the segmentation, and before this we will discuss something about that how to keep a track of the occupied and the free spaces in the memory. So, we have seen that the basic requirement for the execution of the program is that the process should be brought from the hard disk to the RAM. The instructions from the main memory can be read by the CPU directly, and hence we are bringing the process from the hard disk to the RAM. RAM is a faster memory as compared to hard disk, but even though the CPU cannot devote time for accessing the instructions from the main memory directly, so a faster memory known as the cache memory is involved in between the CPU and the RAM. So, a bunch of the instructions is brought from the main memory to the cache memory, and the instructions are executed from the cache memory itself by the CPU, or CPU refers first to the cache to access the instruction, and in case the instruction is not available in the cache, the CPU refers to the main memory, and again a bunch of instruction is brought from main memory to the cache memory. So, we are accessing the cache memory just because we are dealing with the concept of the locality of the reference. The locality of the reference means if one instruction is referenced now, it is likely that the nearby instructions will be referenced later. For example, if I have a program and in this program there are, let us say, 100 instructions. So, in the out of these 100 instructions, if the first instruction is referred just now, obviously the second instruction will be referred next, or most of the time the second instruction will be referred next, and after this the third instruction will be referred next, and so on and so forth. So, if this execution is sequential, the access of the instruction will be like this only. So, why to bring only one instruction at a time to the cache memory? We are actually bringing bunch of the instruction to the cache memory. So, here is a cache memory, and the bunch of the instruction, let us say 50 instructions is brought from the RAM to the cache memory, and the instructions are read by the CPU from the cache itself. So, this is one of the reason why we are bringing the instruction from the main memory to the cache. The other one is that if an instruction is used multiple times in the program, for example, the loop counters are executed very frequently. For example, we are using a loop like this for I equals to 1, I less than or equal to 1000, I plus plus. So, if this is the instruction, then you can see that the I is used 1000 times inside this loop. So, this will be referred 1000 times in this loop. So, we should bring this kind of the instruction also to the cache memory. So, this actually will be referring to the temporal locality of the reference. So, one is the spatial locality of the reference, wherein the nearby codes may be used in the future, and the temporal locality of the reference means that one instruction is being used multiple times in the same program or the process. Whenever we are referring to the read of the instruction from the main memory to the cache memory, obviously a bunch of the instructions will be read, hence we will be providing a range of the addresses that we need to read. So, for reading operation, a series of the addresses is given as an input, and then a read instruction, and in case the writing operation is required to be performed in the main memory, we will again be giving the series of the addresses plus the write instruction. CPU can access to the instruction of the registers in one cycle, but CPU will have to involve multiple cycles for reading the instructions from the RAM. This is because we have to bring lot of data from the main memory. Now, to speed up the process, we already have discussed that we are using the cache, and in case we are using multiple processes in the same memory region, for example, we are doing the partitioning and we are bringing multiple processes in the RAM. So, let us say this is P1 process, this is P2 process, this is P3 process, P4 and P5 process. So, the boundaries of all these processes have been defined. For example, this is the starting address of the P4 process, and let us say 300 is the size of the process P4. So, we need to make sure that the instructions issued for P4 does not lie in the region of P3 and P5. So, we should protect this memory, and this protection can be done with the help of the base and the limit registers. So, the base register contains the starting address of the process, and the limit register contains the size of the process. So, memory protection is required to be performed for every memory management scheme that we are going to use. Now, whenever the CPU refers to any instruction, the CPU considers that the process or the instruction of the process is starting from the 0, or the address of the first instruction is 0, and so on and so forth. For example, if we have the 100 size process or 100 byte size process, the addresses would be from 0 to 99, 0 will be the first address and 99 will be the last address. So, this is actually, or any address in between 0 to 99 will be the logical address. This is also called the virtual address. When we are going to accommodate this process in the main memory, they will be going in any of the region which is free. So, let us say the starting address where it is going is, let us say 7000. So, obviously, the last address will be 7099. So, any address in between 7000, 7000 to 7099 is referred to as the physical address. So, every logical address has an equivalent physical address, and there is a unit of operating system known as MMU, memory management unit, that transforms the address or that maps the address of the logical address to the physical address. Now, any space in between 0 to 90, or the space in between 0 to 99 is known as the logical address space, or all the addresses or set of all the addresses is the logical address space, and set of all the physical addresses will be the physical address space. Now, we have also seen that we can bring any number of the processes in the main memory, but subject to the size of the RAM. CPU can be kept busy for 100% of time only if we bring infinite number of the processes. Otherwise, the CPU will be free for some amount of time. So, to keep CPU as busy as possible, we should bring as many processes as possible in the RAM. So, we will see, or we will suggest the mechanisms by which we can increase the number of processes in the main memory. Then we have seen about the contiguous allocation schemes. The contiguous allocation schemes allocates the space for the process in the contiguous region. It cannot divide the process into the bunches and then allocate the spaces in the scattered region of the memory. The process has to be allocated space in one contiguous space. So, there were two schemes that we have discussed. One was the equal size partition and another one was the unequal size partition. This is the fixed size partitioning scheme where we are fixing up the degree of multiprogramming. In the earlier one, we are fixing the degree of multiprogramming as 4, and here we are fixing the degree of multiprogramming as 5. So, no more than 4 processes can come in this kind of a scheme, and no more than 5 processes can come in this scheme. Here we are fixing the degree of multiprogramming. We also have seen that in the case of the fixed partitioning schemes, there is a disadvantage of the fragmentation, and that fragmentation is the internal fragmentation, because the space being wasted while storage of the process cannot be utilized for storage of the other process. For example, if we take the left hand side scheme or the right hand side scheme, means equal sized and the unequal size partitioning scheme. Let us say we are going to accommodate a process some Pi, and that is a size 404 KB. So, 404 KB process, let us say that has been accommodated with the first fit scheme in this slot. So, 404 K process has been accommodated here in the 500 K partition, and there is a wastage of 96 kilobytes, or 96 K is the wastage of the space. This 96 K wastage cannot be utilized for any other purpose. So, there is a sheer wastage of the memory here in the case of the equal size partitioning and the unequal size partitioning scheme also. We can make use of the dynamic partitioning just to not fix the degree of the multiprogramming and have the effective utilization of the memory. So, this scheme suggests that the entire memory or the entire user space of the memory is treated as a whole, and whenever a job comes or a process comes, the partition is created for accommodating that process, or a whole block is created, or you can say that the partition is created to accommodate that process. Similarly, for the next process also we will be creating, and then for the next process also we will be creating a partition. Okay. If the next partition of let us say 70 kb cannot be accommodated here, then we will wait till another process leaves the space. For example, let us say J2 process leaves the space, and then this J4 process can come in. So, if a hole is created here also, so we will be having two holes now. First there was a hole here, and now after leaving the process J2 and accommodation of J4 is creating another hole. So, a lot of holes will be created when the processes will be coming in and going out. And to understand the disadvantage of this partitioning scheme, means the dynamic partitioning scheme, consider that you have to accommodate a process of let us say 60 size or 60K size, and you have the holes, various holes, let us say H1, H2, H3, H4, let us say this is of size 10, this is of size 5, this is of size 15, and let us say this is of size 30. So, you can see that cumulatively H1, H2, H3 and H4, those are the holes, can accommodate a 60K process, but since they are in the scattered region of the memory, so this is not feasible to store the 60K process in the holes. So, this actually is called the external fragmentation. So, what is the external fragmentation? In case the scattered memory or the scattered holes can accommodate a process when they are brought together, but individually they are not. So, this is the external fragmentation. Fine. So, a lot of holes will be created with the dynamic partitioning schemes. We will see one concept related to this, which is the 50% rule, just a few slides later. But before that, we should also know that to have the knowledge about the different partitions and to know about what is the size of the partition and partition occupied by a process, and what is the size of the partition occupied by the whole. This should be kept a record, or we should keep a record of this somewhere in the main memory itself, or the operating system will maintain this as well. So, there are two schemes for this, one is the bitmap and the other one is the linked list. So, let us say we have a 2 GB of memory, 2 GB of memory, and we are using a bitmap to store the status of all the 16 a bunch of 16 bytes at a time. It means for 16 byte I need a 1 bit. Okay. So, I consider that the main memory is divided into the blocks of 16 bytes. Okay. So, these are all the 16 byte blocks, and then we are considering that the status of each of the block is maintained in the bitmap. If this is occupied, let us say here we have 1, this is also occupied, here we have 1, this is also occupied, let us say we have 1. In case this is not occupied, this is a whole, we will store 0 here. So, for storing the status of each of the bytes in the main memory, we are maintaining the bitmap. Okay. Here we have considered that the status of 16 byte block is stored in the bitmap. Now, let us have a look at what will be the size of this bitmap. Since the status of every 16 byte is stored in the bitmap, so let us find out how many blocks of such kind will be there. So, we have a 2 GB of memory. So, 2 GB can be represented as 2 into 2 raised to the power 10 MB into 2 raised to the power n MB KB and 2 raised to the power 10 bytes. So, these are the total number of bytes divided by 16. So, this comes out to 128 into 2 raised to the power 10 into 2 raised to the power 10. It means this is 128 megabyte. So, 128 megabyte is stored or is used for storage of just the information. So, this is lot of wastage of memory. 128 MB is too much for just for storing the status of the memory. You can also say that since you are storing the status of 16 bytes here in this bitmap, so you can say that 2 GB divided by 16 is 128. So, 2 GB divided by 128 will be 16. Okay. So, here we are saying that the lot of portion or a very big area of the memory is just used just to store the information about the state or status about the partitions. To understand it with a smaller value, then let us say we are storing the status of every 32 bits or 4 bytes in, let us say, the bitmap. So, in that case 1 by 33rd part of the memory will be used to store only the status of the partitions, okay, or status of the memory where the process is there and where the hole is there. In case you need to find out where there is a process and where there is hole, or in case you want to accommodate a process, then what you will have to do, you will have to traverse this bitmap to find out the series of zeros. In case you are able to find out the series of zeros sufficient enough to accommodate your process, then you can accommodate there by setting the bits in the bitmap as 1. Okay. So, this is not a good scheme in both the cases. In case you have to traverse the bitmap, then also it will take a lot of time. Another thing is that a lot of memory space is getting wasted. So, the good scheme would be that we use the linked list for this. So, what is the linked list scheme? Linked list scheme says that you create a linked list for each of the partition. For example, if I am just beginning, there is no process in the system, then I will have only one node, and that will be a hole. Let us say the starting address of that is 0, and let us say some ending address n. So, ending address n is the address of the last block or last byte in the main memory, there is no other than. And let us say a new process is coming. So, a hole will be created and a process will be accommodated in the system. Okay. So, out of this we have splitted this node. So, if this splitting is taking place, here we are storing, let us say, a process. Let us say this is the P1 process, it will have some address starting from 0 and going up to, let us say, m, and then these two nodes are connected. This is a hole, the address of this hole will be starting with m plus 1 and will go up to n. So, you are storing the status in a linked list nodes. So, very few number of the linked list nodes will be created, or you can say that as many nodes will be created as the number of the processes plus the number of holes. So, this will be very few numbers as compared to what we were using a lot of memory in the bitmaps. Now, it is also said that on an average there will be half holes than the processes. Okay, what we are doing that the contiguous holes will be merged with each other. For example, here is the memory schemes where there are some processes and some holes. Let us say this is a process and this is a hole. This is a process and this is a hole. This is a process and this is a hole. Let us say we number these processes as P1, P2, P3. P2 process completes. Since P2 process completes, this will be created or this will be converted as hole. Okay. So, since this is the hole previous to this and hole next to this will be merged together to form a bigger hole. So, we now have a picture of the main memory like this, a bigger hole is there and then a P3 process and then a hole. Let us say P1 process also completes. When P1 process completes, this will again be converted to the hole. So, what we will do, we will merge the hole adjacent to that. So, these two holes will be merged. So, a bigger hole is created and then a P3 process and then a hole. So, here it is noted that the holes are getting merged with each other, and due to merging of the holes, we will say that on an average there will be half holes than processes. On an average there will be half holes than the processes. So, let us say f is the fraction of the memory occupied by holes, and then s is the average size of the process. Let us say the average size of the hole is ks. We just want to find out what fraction of the memory is occupied by holes. So, m is the total memory. In case there are n processes, there will be n by 2 holes. We are considering that there are n processes. So, in case there are n processes, n by 2 will be the holes. N by 2 holes, since each of the hole is having ks size, so n by 2 into ks will be the size occupied by the holes. You can also say that since n is the number of process and average size of the process, average size of the process is s, so holes will occupy m minus ns space. So let us equate this. So what will be the fraction of the memory occupied by the holes? This will be nks by 2, okay, means the memory occupied by the holes divided by the m, that is the total memory. So this is equals to nks divided by 2, and we are replacing this m by this. Let us say m will be equals to n by 2 ks plus ns. We are bringing this part on the left hand side. So this m has been replaced by this. If you take n out and s out, they will be cancelled out and you remain with this part, f equals to k upon k plus 2. So this is the fraction of the memory occupied by the whole, and you say that this is the 50% rule. So what is the 50% rule? On because of the merging of the holes, there will be half holes then process at any given point of time. Now we are going to study another scheme for the memory management. This is known as the segmentation, and segmentation actually is the user view of program. How do you create a program? When you create a program, then there will be some functions, some methods, some array, some table, but when you create the object code, the symbol table will be created, okay. Some of the portion of your program will be going in the stack region. So considering all these, you have said that you have different segments in your process. So all those processes segments may be termed as main, procedure, function, method, object, local variable, common block, stack, symbol table and arrays. So all these are considered as the separate blocks, and we should give the memory to these blocks separately in the main memory, okay. For example, main memory will be given one block of memory, procedure one block of memory, function one block of memory, method one block of memory, and so on and so forth. So this is the segmentation, that we are going to divide our process into the different segments. For example, here the 5 segments have been created, okay. All these segments will be given a number, okay. We have taken this example, all these segments have been given a number. So all these numbers will start from 0, then 1, then 2, then 3 and then 4 if we have 5 segments. So related to every process we will have now the segment number, okay. Now every segment has a particular length, means the size. Let us say the size of these segments is stored in the segment table. So length of each of the segment is given here. Segment 0 has a length 1000, segment 1 has 400, segment 2 has 400 size, segment 3 has 1100 size, and segment 4 is 1000. So these segments are stored in the separate portion of the memory. So non-contiguous allocation schemes we are using here. This is not a contiguous allocation scheme, but the non-contiguous allocation scheme. Now each of the segment is stored in the contiguous blocks. Now means one segment will occupy the contiguous region, then the second segment will occupy the contiguous region, and so on and so forth. So the starting address of 0 number segment is 1400, means segment number 0 will be stored here. Starting address of the first segment is 6300, so segment number 1 will be stored here. Segment number 2 will have the starting address here, segment number 3 will have starting address here and segment number 4 will be having a starting address here. So we are maintaining the segment table that stores the base and the length of each of the segment. So this is actually the overhead for us. So whenever we are referring to the segmentation, we should also refer to the memory protection also. So for the memory protection, we again have the 2 registers, those are storing the information about the base and the limit of the segment, particular segment. So for each segment we will be storing this information. So whenever a CPU refers to some address, for example, CPU is referring to some logical address LA that will be divided into 2 parts, segment number and offset. Offset is what? Segment number 0, 1, 2, 3, 4 as we discussed. Let us see this 0, 1, 2, 3, 4. And what is the offset? Offset is what is the byte referred inside that. Now let us understand it a bit in detail. For example, we are referring to segment number 0, its length is 1000. So, for this segment the first byte is or first instruction is stored in 1400 address, the next instruction will be at 1401, next address will be at 1402, next address will be 1403 and so on so forth. Since its length is 1000, so the last address will be 2399. Okay, last address will be 2399. So, every address should lie in between this. Okay, every address should lie in between this. So, for this only we have this diagram. So, the address is divided into the two parts, segment number and the offset. Offset is telling you that what is the address we are referring to, or it is mostly the length, segment number and then the offset. So, here is the segment table. In this segment table we will first refer to the limit or the size if the offset byte or offset number is less than the limit, it means we are referring to the correct address. For example, if the size of the segment is 1000, the addresses should vary in between 0 to 999, or the offset number should be in between 0 to 999. Even 1000 address is not correct. So, every address referred should be less than the limit or the size of the segment. If not, we will issue the trap or the addressing error. Otherwise, what we will do, we will just add base in this. For example, in this case the base is 1400 for 0 number segment. Okay. So, if we are referring to some address, let us say x, so we should add x 1400 in that. So, that will be giving us the physical address, and the instruction can be read from here and given to the CPU for execution. Fine. Now, what is the merit and the demerit of the segmentation? It is a user view of the process. This is actually the merit. The segment sharing is allowed, means you can create two processes which share the segments. Okay. Then there is a problem of the fragmentation, because when one segment leaves and the other segment arrives for the next process, they may not be of the same size. So, here too we are actually observing that there will be the fragmentation. Okay, and we have to maintain this segment table, so that will be the overhead. It will acquire space in the main memory. Now, let us solve some of the questions related to this. We have the segment table, we have to find out the physical address related to the given logical address. So, logical address is 0, 430, segment number, offset. So, first we should check that for 0 number segment whether 430 is the valid address or not. Length is 700, 430 is less than 700. So, it is fine, there is no problem. We should add the base address 1219 plus the offset, means 430, and whatever this value is, this is the physical address. Similarly, for this 0110, this again is the correct address. So, 1219 base address plus 110, this is the physical address. Okay. Similarly, you can find out for all these. You should just first check if the offset is less than or equal to the given address or not. Fine. So, the last one for today, this is the question which is telling you that which of the following logical address will produce the addressing error. So, addressing error will obviously be there if the limit is being crossed. Okay. So, for example, 430 is well within the limit of 0 number segment. For 1 number segment, 11 number is well within the limit. For 2 number segment which has a length of 100 and we are referring to the address 100. So, this is wrong. Why? This offset should be less than the length, hence it will generate the addressing error or the trap. Fine. Each entry in the segment has segment base, segment peak, segment value, none of the mentioned. So, segment base is there. Okay. The segment base contains the starting logical address of the process, starting physical address of the segment in the memory, obviously starting physical address, not the logical address. Okay. The offset D of the logical address must be greater than the segment limit or 0 and segment limit, in between 0 and segment limit, between 0 and segment number, greater than segment number, obviously 0 and segment limit. Okay. So, this is if there are 32 segments, each of size 1 KB, then the logical address should be, There are 32 segments, so it can be represented like 2 raised to the power 5. So, 5 will be the bits in the segment number, and size of the segment is 1 KB. It means 1024 byte, it means 2 raised to the power 10. So, 10 bits will be required for the offset. So, the total bits will be 15. So, that is all for the segmentation, and we will see the paging schemes from the next turn, and the reference for today's lecture is Operating System Concepts by Silvershire and Galvin. Thank you.